Okay, so looking at the first example shown in the book in number 1.10, assuming a 15 centimeter diameter wafer has a cost of 12, contains 84 dies, and has 0.020 defects per centimeter square. This is another one. Let's see what does he want. Number one, find the yield for wafers. So, let's recall what was the equation of the yield. So, equation for the yield was yield equals 1 over 1 plus defects per area times die area over 2 all square. What do we have here? We have the defects per area. Do we have the die area? Unfortunately not. But we have that the wafer is 15 centimeter, okay? And it the wafer has 84 dies. So if we have the wafer area and the dies per wafer, we can predict the die area. So the die area would be wafer area over dies per wafer, which is in our case wafer area is pi r square. What is the r here? The diameter is 15 centimeter, so the r is 7.5. So it's pi 7.5 square because we agreed that the wafer is circular. Okay, so here we calculated the wafer area. We have the dies per wafer is 84. So by calculating this stuff, I guarantee it's 2.10 centimeter square. So taking this quantity in the yield equation, we can say that the yield is equal to 1 over 1 plus the defects per area, which are 0.020 times the die area, which is 2.10 over 2, taking square here, gets an answer of 0.9093. So we calculated the yield. The next one, he needs the per die for both wafers. So how could we get the cost per die? We said that the cost per die is the cost per wafer over dies per wafer times the yield. So if we get here, what's the cost per wafer? It is 12. So 12 over dies per wafer, which is 84 times the yield we just calculated as 0.9093. That results in 0.1489. So here we calculated the cost per die. Let's see what's 1.10.3. If the number of dies per wafer is increased by 10% and the defects per area unit increases by 15%, find the die area and the yield. Okay, so let's recall that the die area is equal to wafer area over dies per wafer. So what he needs is multiplying the number of dies per wafer by 1.1. 1.1 means that it increased by 10%. So getting here the die area is equal to wafer area, which is pi times 7.5 square again, over the dies per wafer were 84 times the 1.1. That would result in 1.91 centimeter square. So here we got the first thing, which is the die area. So the yield is over 1 plus what? Yes. Area times die area over 2, all of that square. So let's recall that he needs the defects per area to increase by 15%. So we multiply the defects per area by what? By 1.15. So applying to the figures, we have 1 over 1 plus 0.020 times 1.15 times 1.91, which is the number we have just calculated here, over 2, all of that squared, and that would result in 0.9575. Well, here we got the third thing. So, in the fourth one, he says that the fabrication process improves the yield from 0.92 to 0.95. Find the defects per area unit for each version of the technology given a die area of 200 millimeter square. So how could we defects per area? Here we have the yield is equal to 1 over defect per area times the area over 2, all square. A little bit of calculation. We can find that the defect per area is equal to minus square root the yield over square root of the yield times die area over 2. It's just we reformulated the equation to be defects per area. So, applying the numbers we have, one minus 0.92 under the square root over square root 0.92 times 2 over 2. Okay, so why was that 0.92? Because he gave us the yield as 0.92 here. So we just substituted the yield by 0.92 where we have the die area is equal to 2. So that would result in 0.043 defects per centimeter square. Thank you.